Morning, guys. Sir GB again. We will be discussing today the highlights of what the embrace frame or sway frame procedures in the analysis uh, really is. Okay, so what really is the difference between the embrace frame analysis with that of the brace frame analysis? So if we consider a beam column whose ends are free to sway or translate, it is apparent that the maximum primary moment resulting from the side sway is almost always at the ends. Okay, so this is what you need to know. Primarily, one of the major difference uh, between a brace frame and an embrace frame that makes your magnification factor get rid of the value of cm. So cm is always 1.0. That's why the numerator here is 1. Okay, so remember that the derivation of cm is based on the assumption that always the moment maximum lies at the middle, okay, of the and not at the ends. That's why the derivation is particularly coming from the mere fact that we need to represent it by an equivalent moment mv. Okay, so your mj max here is actually at the middle, or simply your m, the magnified moment, is simply at the middle, and it is actually taken care of by this modification factor, which in the unbraced scenario is not very significant. Hence, we always try to make this numerator equivalent to 1.0. So for this, another uh, a situation wherein we look into the ratio given by the alpha here. Okay, alpha. Originally, it's simply a p over p equation. So, but for unbraced frame, it is already a summation of the uh, individual column strength or capacity with that of the summation, okay, of the elastic buckling strength. So the premise of such modification or change is such that the behavior of each column will affect the other columns in the story, because it's already embraced whatever sway behavior that this column experience will be experienced by the other column adjacent to it. Okay, so you do not talk of braced columns now. You are actually talking of unbraced frames. So the frame means all the columns constitute the bracing. Okay, take a note that the summation of p, this is the capacities for LRFD is simply the summation of PU, but for ASD there is a an increase, no, in the allowable capacities by 1.60, no, just to differentiate what summation of P is for LRFD and ASD. And the summation of the Euler backling strength can actually be determined by another formula on the basis of side sway buckling analysis, and this is the other way of determining summation of PE, where this is equivalent to RMHL over uh, the Greek letter H. Okay, so this is, I think, I forget the Greek letter, but it seems that this is the equivalent for the Greek letter H. Okay, so this 1 minus 0.15 of PMF, where PMF is the sum of the vertical loads in the story, which is a part of the MRF. So in this particular situation, we can surmise that if you want one column to be out of the uh, participation in resisting the lateral forces, you can do it. No, so you can only choose the columns uh, upon which your resistance for lateral swaying is concerned. So you have a choice to what columns constitute the MRF, or the moment resisting frame. So if you want your columns to be only a dummy column that only resists actual loads, then you have the choice to do it. L is the story height. I think this is eta, no? Eta is the interstory drift, and H is the story shear. Okay, the sum of the horizontal forces causing the drift. So take note that the summation of PE can also be determined using the Euler elastic backlink formula. So this is a pi squared EI all over KL squared. So note, if MNT and MLT acts at a different point along the member, then AISC equation or the magnified moments produce conservative results. So which means to say that if the brace part scenario, let's say this is now your brace part, and your unbraced part scenario, which has this as your P delta, no? The P delta there and the P delta here, wherein the maximum moments may not be at the same point. Let's say this is the point wherein this is the maximum moment here, it's the point of maximum moment, or maybe here the point of maximum moment is there. We don't know. So then still your results produces conservative values. From the figure below, the moment MNT in the member is computed by using only gravity loads, and because of symmetry, there is no bracing required to prevent the side sway. So this moment is amplified to a factor of B1 to account for the P delta effect, and in case of MLT, the moment corresponding to the sway will be amplified by B2 to account for the P delta, big delta effect. Okay, so hence the magnified moment, the MR, may be computed by using this formula. So this is now the formula for MU magnified. Okay, MU magnified is simply the one that you will be using on your interaction diagram, which is the required MR that we are talking about here. Okay, so this is the figure that shows you asymmetrical frame, wherein there's no need to put an AJR here or an artificial joint restraint, because this will be braced. No? When H is not acting on it, I'm sorry, I have to put this brace. Okay, so when H is not acting, you don't need to put a brace here to make it a brace frame, so no need, no? But if this is unsymmetrically loaded or unsymmetrically framed, configured, then you need an artificial joint restraint to make it a brace frame, and then apply H alone without the vertical load to make it an unbraced frame. So this is now the decomposition of the frame to represent the primary frame or the original frame we are considering. So this is what I'm talking about. If the loads are not symmetrically placed, then you need an AJR to tackle the MNT, the no translation effect, and the with translation effect. Okay? So if this is a multi-story structure, then you have to uh, uh, have a procedure or a process on how to determine the AJRs for you to apply them, okay, uh, on the MLT conditions. So in case there's an additional edge here coming from somewhere lateral, then you have to consider H then, in addition to the AJR that you placed on the brace condition. So in summary, class, okay, in summary, a brace frame analysis will constitute an MNT only, okay, while an unbraced frame analysis will constitute an MNT and an MLT uh, simultaneously. Okay? So when you say you have an unbraced frame, you are not, you have to get rid, or you have to consider both the no translation behavior and the lateral translation behavior. And I make a summary of how the unbraced frame works. So first step is to divide the model into two parts, the gravity model and the lateral load model, okay, as described on the figure. Then we analyze the model frame for both gravity and lateral translation. So the analysis may be a direct analysis, first order analysis, or an approximate second order analysis. So number 3, apply appropriate load combination in LRFD or ASD. Okay, and normally for the load combination on the lateral part, the wind and the earthquake loads are the most common, no? Commonly placed loading. So for number 4, step solve for the column and the beam strength using column and beam concepts. Okay, so this is a concept on compression members and flexural members. Okay, compression and flexure. Compute the moment magnification factors as per AISC rules and guidelines and apply the interaction equations. Okay, I'd like you to study the example 6.6 to better give you an idea of what the procedure is all about, and I will be giving you some uh, problem sets to consider in relation to this topic on frame analysis. Thank you very much for listening. Have a nice day and God bless you.